The question is where you want to incorporate the assumption and when you want to incorporate the assumption. You could incorporate the assumption after you write the generalized model. Now, this generalized model does not include the assumption that the cross-sectional gradient is negligible, and this is the way to do that. You cannot arbitrarily neglect the second order derivative in the Laplacian because the boundary condition is now going to be different. And the way to see that, to appreciate that is, I would probably urge you all to take a look at the solution of two different types of problems. One is, you take a diffusion operator and you put zero boundary conditions, okay, Dirichlet or zero boundary conditions, and you take the same problem, put zero flux boundary condition, and you take the same differential operator and put a two flux boundary conditions, okay, like something like this. And you have to convince yourself that the nature of the solution you get in all these three are completely different. Particularly in the third case, it will be completely different. If you want me to state it, so I would like you all to convince yourself by solving this problem. You solve d square t by dx square equal to 0 with three types of boundary conditions. You can say t at x equal to 0 equal to t at x equal to 1 equal to 0, okay, that's one problem. And then you say dt by dx at x equal to 0 equal to dt by dx at x equal to L equal to 0, that's the second problem. And the third one is dt by dx at x equal to 0 equal to sum h into h by k into t at x equal to 0 minus t infinity, and dt by dx h by L into t at x equal to L minus t infinity. That's the third problem. One could in principle have mixed boundary conditions. You should actually even try to solve that also, and you must appreciate that these three classes of problems have completely different solutions. And in fact, if you understand that, that's the reason why you cannot incorporate this assumption directly into the generalized model, and this is the correct way to incorporate the assumption that the gradients in the radial direction is 0, particularly when you have this kind of a convection or flux boundary condition. If you have these two types of boundary condition, then you would assume you can directly ignore the gradients and you would not make a mistake because of the nature of the solution that you will get for these three types of problems. It's a very good exercise. All of you should actually try to solve these three types of problems, and you will see these three classes of problems in almost all the engineering systems that you will see in this program and also probably elsewhere. It's a very, very common type of differential equation problem that you will see in many, many engineering systems. And there are some very good reasons for that. I will not get into that, but there are very good reasons why these classes of problems will appear in almost all the natural systems that you will try to model. Assuming cross-sectional area temperature to be uniform is not an appropriate and not a realistic thing if the aspect ratio is reasonably good. If the aspect ratio is very small, then you can assume that the temperature is almost uniform. Now, of course, you don't have to assume that to be uniform. It just makes your life easy to solve the problem, that's all. Now, you could in principle take the full problem and get the full solution, and you will see that the solution that you will get from this equation will not be very different if you impose the condition that the temperature is nearly uniform in the cross section. It doesn't matter. You can go either way. It doesn't matter. You can start from the generalized equation and then you can integrate, you will get exactly the same. And you can start from, you incorporate the assumptions while building the model, you will get exactly the same equations. It wouldn't matter. And in fact, some of your things about the integral balance is already incorporated here. This is exactly what you do when you write an integral balance. Okay, so let's take one of the questions that he asked. What happens if x is constant? Before that, we should actually go to the boundary conditions of this problem. So in principle, there are four different possible boundary conditions that you could have. One is, obviously you can have a flux boundary condition, dt by dx at x equal to L will be h t at x equal to L minus t infinity. So that's one possible boundary condition that you would obviously guess that just like how heat transfer is occurring from this cross sectional area, you would expect that the heat transfer would occur from the other edge of the fin as well. Now, the second possible boundary condition is that there is no flux, maybe that section is insulated. So, if the boundary is insulated with some insulator, then there is no heat exchange, that is you impose an adiabatic condition at the other end of the fin. And then the third one is you could impose a constant boundary condition. So, this is very unlikely, but just for hypothetical case you can assume that T at x equal to L is some constant temperature. There are some examples, but there are not that many. And the fourth one, which is generally used for some standardization purposes. So, supposing if the fin is infinitely long, fin, what will be the boundary condition? If the fin is infinitely long, you want to try? If this fin is infinitely long and if the temperature of the fluid is T infinity, what would you expect? T equal to T infinity, right? So, you expect that T at x equal to L, L tending to infinity will be equal to T infinity. So, that is just for standardization purposes. You will never achieve such an ideal situation however long the fin is going to be, but it is just for standardization purposes such kind of boundary condition has been prescribed. Okay. Alright, so next we go to a specific case where, so supposing we assume that the cross sectional area is constant, so which means that the cross sectional area is same and therefore the curved surface area is actually a curved surface area of a cylinder. So this equation would simply, which means that dAcx by dx is 0, which means that the gradient of the cross sectional area with respect to x is 0 because it is a constant, and so we can simply reduce this equation as d square t by dx square, that is equal to h by k AC t minus t infinity. What is dAs by dx for constant cross sectional area? It's 2 pi r, perimeter, right? It's the perimeter. So, if P is the perimeter, P is the perimeter of the fin that you are considering, and that should be equal to dAs by dx. The change in the cross sectional surface area for heat transport is simply the perimeter of that particular fin. How do I solve this equation? Is it complete? Do I need to know something else to solve the equations? I need to know the boundary conditions, right? So, if I specify the boundary condition that x equal to 0 is the temperature of the base, okay. So, note that the fin is attached to a base surface, and so if the temperature of the base surface is specified, so that is going to be the boundary condition at x equal to 0, and I could say that T, if I assume that there is a convection boundary condition, so if I specify this boundary condition, then we can solve the equation. How do we solve this equation? How do we solve this? Yeah, not that hard. Some exponential. So, you say theta is t minus t infinity, you make a substitution, and then this will become d square theta by dx square equal to, if I call this m square theta, and this will be theta at x equal to 0 is Tb minus T infinity, which I can call it as theta b, right? Did I get it right? So, theta is T minus T infinity, right? So, okay, and then minus k d theta by dx at x equal to L, that's equal to h into theta. So, it's a pretty easy, and you can solve this. This is exponential solution. It's like an eigenvalue problem. What are the eigenvalues of this differential equation? Eigenfunctions? Eigenfunctions are e power, plus mx and minus mx. So, you can solve the eigenvalue problem and substitute the boundary condition. I will just give you the final form. So, theta x by theta b, which is the base temperature, is given by the ratio cos m L minus x plus h by m into k into sine hyperbolic m L minus x divided by cos hyperbolic m L plus h by m k sine hyperbolic m L. Okay. So, that is the solution, and the profile will be, so if theta b, that is the profile that you will expect. So, that is the profile that you can expect from this solution, and in fact you should go and plot this and see. It is sort of obvious to read it out if you know how cosine hyperbolic and sine hyperbolic functions look like, but if you do not know, I think it is a good exercise to go and plot cosine and sine hyperbolic and convince yourself that this is the solution for this kind of a problem. Okay. So, now we said that when we started this extended surfaces problem, we said that the purpose of extended surface is essentially to increase the heat transfer rate, right. So, therefore, we need to find out what is the total heat that is transferred by the fin. Okay. So, that is the quantity of interest which is going to quantify the problem that you are looking at. So, we need to find out what is the total heat transfer rate. How do we find this? How do we find the total heat transfer rate, that is the total amount of heat that is transported by the fin? So, note that there are two processes. One is it is transferring by conduction and the heat is being lost from the other end of the fin, and while doing that it is also simultaneously losing heat via convection. So, how do we find the total heat transfer rate? Yeah? They are supposed to be added how? So, one could integrate h into dA s into t minus t infinity, okay, across the whole fin. So, that will give you the total amount of heat that is transferred. So, that is one way to do that. But so note that I always told you that you should use your intuition. So, there is an intuitively simple way to do this, okay. So, we assume that the system is under steady state, right. We said that the system is under steady state conditions. So, if it is under steady state conditions, it means that the temperature profile remains constant, right, it does not change with time. So, whatever heat, so supposing if this is my fin, because I impose a steady state condition and there is no heat generation inside, so whatever heat that is actually transferred to the fin at the base should be equal to whatever total heat that is being transferred, right. So, it is a very simple thing. Is that clear to everyone? Whatever is the total amount of heat that is transferred from the base to the fin should be the total amount of heat that the fin is able to transfer. Because I said it is a steady state condition, the temperature profile has to be maintained. So, whatever heat that comes in should actually go out, otherwise the temperature profile is going to change. Our assumption is not valid. So, So, in order to satisfy the assumption that we made that it is under steady state conditions, an intuitive way to find the total amount of heat transfer is what is the amount of heat that is actually transferred from the base to the fin at x equal to 0. And in fact, if you integrate, you will find that it will be exactly the same. Okay, and that will be give you the expression. So, that will be minus k. So, the total amount of heat that is transferred by the fin Qf is minus k into cross sectional area into dt by dx at x equal to 0. So, that is the amount of heat that is transferred to the fin at x equal to 0, and that should be equal to the total amount of heat that is transferred, and so that will be equal to and that should be theta b square root of hp kc kac into sine hyperbolic ml plus h by mk into cos hyperbolic ml divided by cos hyperbolic ml plus h by mk sine hyperbolic ml. Okay. So, that is the total amount. So, note that it is the total amount of heat that is transferred. The local heat transfer rate is not constant. So, remember the when we discussed about the resistances, that whenever there is heat generation or heat loss at local location from the solid that you are looking at, the total heat, the local heat transfer rate is now going to be a function of position. And in fact, that is sort of alluded to in this expression. So, note that the total heat transport rate is now a function of the length of the fin that you are considering. If it were to be constant, then irrespective of the length, the heat transfer rate should be exactly the same. That is not true. So, it is a function of the length, and in sort of it is reflected in the total heat transport rate. So, if you know the length of the fin, then you should be able to calculate what is the total amount of heat that particular fin can actually transfer from the base. And this is an important design parameter. So, you have, if you know what is the total amount of heat that you want to transfer, then you could use this expression in order to design the length of the fin. So, this is often an important parameter that you have to find. What is the length of the fin that you have to use in order to achieve a certain amount of heat transport rate? Is that clear to everyone? Okay. So, I will just give you the expressions for the other type of boundary conditions, but I would strongly encourage you to derive them and convince yourself. So, supposing if you use no flux boundary condition, so that is the second type of boundary condition, dt by dx at x equal to L is 0, and the solution will be theta by theta b is cos h m L minus x divided by cos hyperbolic ml, and the total heat transfer rate Qf is given by square root of hpk times AC into theta b into tan hyperbolic ml. And for the third boundary condition, where you have a fixed temperature, that is theta at x equal to L is theta L, the solution will be theta by theta b equal to theta L by theta b multiplied by sine hyperbolic mx plus sine hyperbolic ml minus x divided by sine hyperbolic ml. And for the fourth type of boundary condition, where you have long fin, infinitely long fin, so theta at x tending to infinity, that is equal to 0, that is the temperature on the other end is equal to the temperature of the fluid itself, and so that case theta by theta b is simply given by e power minus mx, and Qf is given by square root of hp kac into theta b. So those are the 4 different solutions, and I would encourage all of you to actually derive these expressions and convince yourself that this is the solution. Okay. So there is another definition and some expression for the definition. With that we will finish today's lecture. What is called the efficiency So note that when we said the purpose of a fin is basically to enhance the heat transfer rate. So therefore from design point of view, it is useful to define a quantity called efficiency. How efficient is the fin that I have designed? Can I calculate the efficiency and find out what, so if I want to compare two different fins, instead of comparing what is the actual total heat transfer rate, it is useful to compare the efficiency of the fin that has been designed. So therefore the efficiency of a fin is basically defined as the total heat transport rate, that is the total amount of heat that is transferred by the fin divided by the maximum possible heat that can be transferred, divided by the maximum possible heat that can be transferred by the same fin. What is Qmax? How can we find the maximum possible? So let us pose a slightly different question. When can we achieve maximum heat transfer from a fin of a given geometry? When can we assume, when can we get maximum heat transport rate? Under what conditions? Temperature? But that's like an infinitely long fin, you're never going to achieve it. In fact, if the temperature at the right end is T infinity, then the temperature gradient or driving force for convection is almost 0 at the end of the fin. So which means that the end of the fin is almost of no use. See, any heat transport rate is governed by the temperature gradient, which is the driving force. So if the temperature at the end of the fin is equal to that of the fluid temperature, it's no use. So you don't want to design a system where some parts of your fin is going to have a 0 driving force. That's useless. It's a waste of money. Okay, so how do we find maximum? When do you achieve maximum heat transfer rate? It's hypothetical, you're not going to achieve it. Temperature is constant where? Throughout the length. Okay, what is that constant? That's equal to the base temperature. Okay, so what's the purpose of a fin? The purpose of a fin is to transfer heat from the base to the fluid around. So when can you achieve maximum heat transfer rate? When the temperature in the fin is constant, and not just at any constant, it should be equal to the temperature of the base itself, because that's the maximum possible heat that you can transfer. So therefore Qmax is simply given by H into the overall convective heat transport area multiplied by Tb is the base temperature. So the maximum possible rate, so not that this is maximum possible rate, but what you will actually achieve in reality will obviously be lesser than this. So this is the maximum possible, and therefore one can define efficiency as Qf divided by HAS into Tb minus T infinity. So that's the efficiency of a fin, and in fact for this problem the efficiency would be so for the second type of boundary condition where it's an adiabatic case, so eta f simply given by square root of hk perimeter into AC into theta b tan hyperbolic ml divided by h into as into theta b. Theta b is nothing but Tb minus T infinity. So that's the substitution that we made when we solved the differential equation, and so that's nothing but tan hyperbolic ml divided by ml. Okay, what happens when L equal to 0? Yeah, what is tan ml by ml when L equal to 0? Okay, what is tan hyperbolic when L is 0? Yeah, 0. So it is 0 by 0. So what is it? No, it's not that simple. How do you know that it's 1? When you have an indeterminate system, what do? You do an L'Hospital's rule, and so you will find out that eta f is equal to 1. That's sort of obvious to intuit. And the reason why you can intuit is, you said that the maximum temperature in the fin is achievable only when the fin size is 0. You can never achieve a constant temperature which is equal to the base temperature. So therefore, the efficiency, if at all you have the base cross sectional area which is sufficient to transport heat as much as whatever is required to be transported, then the efficiency is going to be 1. But this is not a realistic case, it's just hypothetical. Yes? It will be 0. That's right. So which means that as L goes to infinity, eta f goes to 0. That's right. So it's not that you design a long fin and you're going to have very high heat transport. So it's completely counterintuitive. So although intuitively you would guess that I design a very long fin and I'll be able to achieve as much as heat transport that I want, that's not really true. And the reason why the efficiency is very poor is that as the length increases, the driving force is constantly decreasing, because you have two processes which are occurring simultaneously. One is the conduction and the other one is the convection. So it's the driving force which is actually forcing the efficiency to be 0.